Hello and welcome to a second lesson on the differentiation of polynomial functions. This lesson follows on directly from the first lesson. For the second part of this lesson, we're going to investigate stationary points of polynomials. Now there are three types of stationary points. We can have what we call a maximum point, where the curve is increasing in value up to a maximum and then starts decreasing. Or we can have a minimum point where the curve is decreasing to some minimum value and then starts increasing. Or we can have a point of inflection, which is where the curve is increasing but levels off to zero gradient and then starts increasing again, or is decreasing, levels off to zero gradient and then starts decreasing again. Let's have a look at an actual graph of a polynomial function. This one is y equals 2x to the power 6 minus 4x to the power 5 minus 2x to the power 4 plus 4x cubed plus 2. And we can see that it's got two minimum points, one there and one there. It's got one maximum point there. And it's also got one point of inflection where the gradient is positive, becomes 0, and then is positive again. So what we need to do now is look at how to identify a stationary point. We can identify a stationary point by looking at where dy by dx is equal to 0, because at a stationary point the tangent of the curve is horizontal, and so dy by dx is 0. So in order to locate these stationary points, we differentiate the equation of the curve to find dy by dx. We set dy by dx equal to 0 and solve that equation to find the values of x where dy by dx is 0. The next task is to decide what kind of stationary points they are. Are they maxima, minima, or points of inflection? And that's what we're going to look at now. Look at a maximum first. The gradient here before the turning point is positive. The gradient at the turning point is 0, and the gradient after the turning point is negative. And we can see how a maximum fits in between those gradients. So if we can test just before the turning point and just after the turning point, and we get positive gradient followed by negative gradient, then we have a maximum. On the other hand, a minimum, just before the turning point, the gradient is negative. At the turning point, it is 0. And after the turning point, it's positive. And again, we can see how the minimum fits in between those three lines. So if we test just before the turning point, or the stationary point, and we get a negative gradient, and we test just after we get a positive, then we have a minimum. Points of inflection, we can either have positive before the stationary point, and then we have 0 followed by positive, or we can have a negative gradient, then 0, and then another negative gradient. So by just looking at the gradient of the curve just before and just after the turning points or stationary points, we can determine what kind of stationary point it is. Now that's a lot of testing to be done, and often there's a better way of doing it. And what we can do is we can look at something called the second derivative. That's d2y by dx squared, and that's just dy by dx differentiated again. Now let's suppose that this second derivative is negative, it's less than 0. That means the gradient of dy by dx is negative. So dy by dx is decreasing if its gradient is negative. Well, if it's decreasing through 0, then what must be happening is it must be positive, then 0, and then negative. That's the only way it can be decreasing as it goes through 0. So what we have here is a maximum if d2y by dx squared is less than 0. So let's label that one. That gives us a maximum. Now then, what if d2y by dx squared is positive as we go through a stationary point? That means the gradient of dy by dx is positive, which means dy by dx is increasing. If it's increasing through 0, it must be negative, then 0, and then positive. So we have a minimum point on the curve. So if the second derivative is positive when dy by dx is 0, we have a minimum, and if the second derivative is negative, we have a maximum. And you need to learn those two facts. They're perhaps counterintuitive to what you might have thought. Negative gives you a maximum, positive gives you a minimum. Perhaps your gut feel would be the other way around. What about when d2y by dx squared is equal to 0? What can we decide from that? Well, unfortunately, we can't decide anything. We can't tell from that whether it's a minimum, a maximum, or a point of inflection. Let me show you an illustration of why. Let's look at these curves y equals x to the power 4, y equals minus x to the power 4, and y equals x cubed. And I've got sketches of the graphs here. Here's the graph of y equals x to the 4, here's the graph of y equals minus x to the 4, and here's the graph of y equals x cubed. Now let's suppose I find dy by dx. dy by dx is equal to 4x cubed. And d2y by dx squared, if I differentiate again, is equal to 12x squared. Now then, what if we consider when x is 0? Well, when x is 0, putting 0 in here, dy by dx will be 0, so we have a stationary point. d2y by dx squared will also be 0 when I substitute 0 in. So what I've found here is when x is 0 and the second derivative is 0, I've got a minimum. Well, let's move on to the next one. For this one, dy by dx is minus 4x cubed, and d2y by dx squared is minus 12x squared. Now again, if we look when x equals 0, we'll see that dy by dx is 0, so we have a stationary point, but the second derivative is also 0. But this time we have a maximum. So, if the second derivative is 0, how can I possibly know whether I've got a maximum or a minimum? It gets worse, because we can also have a point of inflection. Let's consider this curve. dy by dx would be 3x squared, and d2y by dx squared is equal to 6x. Again, if we put x is equal to 0 in there, dy by dx is 0, so we have a stationary point, but the second derivative is also 0. Yet I've got a point of inflection. So with these three examples, we can see that when we've got dy by dx is 0, and there's a stationary point, and when we've got d2y by dx squared is 0 as well, we might have a maximum, we might have a minimum, we might have a point of inflection. So it doesn't help us at all. In that case, we go back to the previous method I've talked about, testing just before and just after the stationary point to see what kind of stationary point it is. We'll now use two examples to illustrate the techniques we've been discussing. The first will be very simple, just using a quadratic function. The second will be more involved, typical of an exam question, using a cubic function. So example 2. Find the stationary point of the curve y equals 2x squared minus 12x. Indicate the nature of the stationary point and sketch the graph. So we begin with the function itself. Y equals 2x squared minus 12x. And we first differentiate to find dy by dx. Differentiate 2x squared, we get 4x. differentiate minus 12x, we get minus 12. Now at a stationary point, dy by dx equals 0. So at stationary point, dy by dx is equal to 0. And that implies that in that case, 4x minus 12 is equal to 0. So 4x is equal to 12. X is equal to 12 divided by 4. So x is 3. And that gives us the x-coordinate of the stationary point. But we still need to find the y-coordinate. When x equals 3, y is equal to, and we simply substitute the 3 in the y function, so it's 2 multiplied by 3 squared minus 12 multiplied by 3. So y is equal to 3 squared is 9, 2 9s are 18, 12 3s are 36, so it's minus 36. So y is equal to 18 minus 36, which is minus 18. So we can now say that there's a stationary point at the point 3 minus 18. We'll now use both methods to indicate what kind of stationary point it is. We'll begin with the method where we test dy by dx just before and just after the stationary point. So dy by dx is 0 when x is 3. So let's look when x is 2.9, just before 3. Just less than 3. When x is 2.9, dy by dx is equal to 4 multiplied by 2.9 minus 12, which is equal to 11.6 minus 12, which is minus 0.4. So dy by dx is negative just before the stationary point. Now let's look just after. When x equals 3.1, dy by dx is equal to 4 multiplied by 3.1 minus 12. Now 4 times 3.1 is 12.4, and 12.4 minus 12 is equal to 0.4. And more to the point, it's plus 0.4. So dy by dx is positive just after the stationary point. So we have a situation where we've got a negative gradient before the stationary point. At the stationary point itself, the gradient is 0. And after the stationary point, the gradient is positive. And we can see that that actually describes what happens when we have a minimum point. So I can now say that we've got a minimum point at 3 minus 18. And we'll now go on to look at the same thing using the second method, the second derivative. If dy by dx is equal to 4x minus 12, then d2y by dx squared, simply differentiate again. We differentiate 4x, we get 4. Differentiate minus 12, it's 0. So d2y by dx squared is 4, or let's say plus 4. And it's not dependent on x, it's always plus 4. So that means at the stationary point, the second derivative is positive, and the rule for that is if the second derivative is positive, we have a minimum. So I can say, therefore, there's a minimum at 3 minus 18. And finally, for this question, we sketch the graph. I can see that there's no constant term, there's no y-intercept, so it's going to go through the origin, and the graph's going to come down like this and back up, and the minimum point here is 3 minus 18. We could mark on the origin there, we can see it goes through there, and I could actually, because of symmetry, the line of symmetry that a quadratic graph has, I could actually mark that point as 6. Because if 3 is the minimum point, then that would be 0, and that would be 6, 3 either side of it. And that concludes example 2. We'll now complete the lesson with example 3, which is typical of an exam style question. Find the stationary points of the curve y equals 2x cubed minus 3x squared minus 12x plus 10. Indicate the nature of the stationary points and sketch the graph. So we begin with the function. Y is equal to 2x cubed minus 3x squared minus 12x plus 10. Differentiate to find dy by dx, and we get 6x squared minus 6x minus 12. Now at a stationary point, dy by dx is 0. So at a stationary point, dy by dx is 0, which implies that 6x squared minus 6x minus 12 is equal to 0. Now we want to factorize this, but first we can see there's a common factor of 6 running through, so we can divide by 6 and get x squared minus x minus 2 equals 0. And now we can factorize that easily. We want two numbers that multiply to minus 2 and add together to minus 1, which would be minus 2 and plus 1. And if the first bracket is 0, x equals minus 1. And if the second bracket is 0, x equals plus 2. Now we need to find the y coordinates. So when x equals minus 1, y is equal to 2 times minus 1 cubed minus 3 times minus 1 squared minus 12 times minus 1 plus 10. What does that give us? Minus 1 cubed is minus 1, 2 times minus 1 is minus 2. Minus 1 squared is plus 1, minus 3 times plus 1 is minus 3. Minus 12 times minus 1 is plus 12, and finally plus 10. So we've got 22 positives, 5 negatives, so that comes to plus 17. So we've got a stationary point at minus 1, 17. And when x equals 2, the other value where dy by dx is 0, y is equal to 2 times 2 cubed minus 3 times 2 squared minus 12 times 2 plus 10. 2 cubed is 8, 2 times 8 is 16, 2 squared is 4, minus 3 times 4 is minus 12, minus 12 times 2 is minus 24, plus 10. This time we have 26 positives, 36 negatives, so that comes to minus 10. So we have a stationary point at 2, minus 10. And from here we'll go on to use both our methods for identifying what kind of stationary points these are. This time we'll begin with the second derivative method to show what kind of stationary points these are. And you'll see how easy it can be. So find the second derivative, d2y by dx squared. Differentiate 6x squared, we get 12x. Differentiate minus 6x, we get minus 6. Differentiate minus 12, we get 0. And I'm now going to look at d2y by dx squared when x is minus 1, the first stationary point, and when x is 2, the second stationary point. when x equals minus 1, d2y by dx squared is equal to 12 multiplied by minus 1 minus 6, which is minus 12 minus 6, which is minus 18. And of course minus 18 is negative, it's less than 0. If the second derivative is less than 0 at a stationary point, we have a maximum. So I can say therefore a maximum at minus 117. Turning to the second stationary point, when x equals 2, d2y by dx squared is equal to 12 multiplied by 2 minus 6, which is 24 minus 6, which is plus 18, which is greater than 0. And if the second derivative is positive at a stationary point, we have a minimum. So I can say therefore a minimum at 2 minus 10. We'll now look at the alternative method for determining what kind of stationary points we have. We'll look at dy by dx before and after the stationary points. So if we look at the stationary point where x is minus 1, just before minus 1, we can say when x equals minus 1.1. And in that case, dy by dx is equal to 6 times minus 1.1 squared minus 6 times 1.1 minus 12. And if we put that in the calculator, we get 1.86, which is greater than 0, so it's positive. If we move just to the right of the turning point, when x equals minus 0.9, so I'm just adding 0.1 on to the minus 1, in that case, dy by dx is equal to 6 times minus 0.9 squared minus 6 times minus 0.9 minus 12. And that comes to minus 1.74, which is less than 0, it's negative. So we have a situation here where as we go from left to right through the turning point, through the stationary point, we've got a positive gradient, then at the stationary point it is 0, and then after the stationary point it's negative. And that describes a maximum. So we have a maximum at the point minus 117. Same again for the other stationary point. Let's look just before 2 and just after 2. So when x equals 1.9, just less than 2, then dy by dx is equal to 6 times 1.9 squared minus 6 times 1.9 minus 12. Put that in the calculator and we get minus 1.74, which is less than 0. In other words, it's negative. Now let's look just after 2, when x equals 2.1. dy by dx is equal to 6 times 2.1 squared minus 6 times 2.1 minus 12. And if we put that in the calculator, we get 1.86, which is greater than 0. In other words, it's positive. So the situation this time as we go from left to right through the turning point is we have a negative gradient, then at the turning point itself the gradient is 0, and then we have a positive gradient, and that describes a minimum point on the curve. So we have a minimum point at 2 minus 10. Now, rather more work involved in doing that than there was finding the second derivative. So for polynomials in particular, it's a good idea to use the second derivative method and only use this if the second derivative turns out to be 0. Right, now we'll sketch the graph. Well, we've discovered there's a maximum point at minus 117, so we can mark that there. I'll say that's 17. And there's a minimum point at 2 minus 10, so we'll put that down there. And we'll mark on here minus 10. And now the graph comes from down here as a maximum point at minus 117, and then comes down to a minimum point at 2 minus 10, and then off it goes towards infinity. The only other point we could mark on the graph would be the y-intercept. I can see that there's a y-intercept of plus 10, so I could mark 10 on there. And that completes the question. It also completes the lesson. We've now had a good look at finding stationary points and identifying their nature. There'll be an exercise for you to do now to let you practice these techniques, and I suggest you use both the second derivative method and the method where you look at dy by dx before and after the turning points, because in the exam questions you could be asked to use either. You won't necessarily have a choice.